Hello everyone, welcome back to ECE350, Chapter 6, Lecture 13. In this chapter, we're going to talk about time-varying magnetic field and electric field. So first is time-varying magnetic field. So let's see what is time-varying magnetic field. If your magnetic field it could be B or could be phi, could be H. So there's few things you can do. It could be B, H, or phi, which is magnetic flux. Uh, if they're changing over time, that's called time varying field. If the change is what happened, that's the main thing for the chapter here. So the electric field, um, when you have current, then you have magnetic field, right? So when current goes through a conductor, there's a magnetic field around it, and if that is time varying, your magnetic field will be time varying also. As long as your charge and current distribution remain constant, your magnetic field does not change either. So when your magnetic field and electric field combine together, we call them electromagnetic field, and that produce electromagnetic waves. That electromagnetic waves, we have seen the many applications of electromagnetic waves in our daily life, like say X-ray, infrared, gamma ray, radio waves, and light, and so on. So those are all electromagnetic waves. We're going to talk about this electromagnetic waves propagation, how they propagates in next chapters. There are few fundamental rules we know we have in electricity and magnetism. We have Gauss's law, we have Ampere's law, we have Faraday's law, and others laws together. So those are all in their own places. They're very important laws. But what Clerk Maxwell did, he basically put all those laws together and say this is the relation between them. So his works called Maxwell equations. Like for this one and this one, if you can see that basically represents your Gauss's law, and the second one it represents Faraday's law, and fourth one represents Ampere's law. So we're going to go through them, all of them. To understand this, you have to understand the symbols here. E and D, they're basically electric field intensity and electric flux density. And relation between them is D to epsilon E, where epsilon is permittivity. And you have seen them in physics 260. And B and H, B is the magnetic flux density, H is the magnetic field intensity. And relation between them, B equal to mu H, and mu is the permeability. All right. And rho V is the electric charge density, and J is current density. So you have seen them in your physics 260. So these are the relation between them. Now, if I go into differential form and integral form, this is the differential form over here. The original form of Maxwell equation all are in differential form. If you take the integration of that over a closed surface, you get the total charge, right? And also, this is the again this one using over here. This one using your divergence law, divergence theorem. This is the relationship happened due to divergence theorem. Oops, divergence. And this relation happens because this the relation over here is Stokes theorem. We talked about it in chapter 3. And this one again, divergence theorem over here. And this one, again, Stokes theorem. So this one is Ampere's law. This is the differential form, and this is the integral form. All right. So we're going to talk about this, all four of them together in these chapters, because we cannot separate them when there is a time varying component, like when your d by dt is not zero. If d by dt is zero, then electricity and magnetism are separated. Okay. So the first connection between electricity and magnetism was discovered by Ørsted, and he saw that your compass deflect when it comes close to current carrying conductor. That's the first observation he made. Then since then, there's no reversal of that. Let's see. Okay, electricity produce magnetic field, but can magnetic field produce electricity? So that is the hypothesis of Faraday's work. He said, okay, if electricity produce magnetic field should be able to produce um, uh, electricity. That's the hypothesis for Faraday. And to test that, he made this experimental setup over here. So he observed it for 10 years to see. So he has is battery, right? And he has the current carrying conductor here, and that produces magnetic field. So he has another loop over here trying to catch that magnetic field to produce electricity. He was trying to see is any deflection in the galvanometer. If you have a deflection in galvanometer, that means you have electrical signal there. But 10 years, nothing happens. So one day he was trying to change the battery here from old one to new one, and the moment of change, he saw that galvanometer is deflecting. So then he did it, and again. Every time he trying to connect a new battery, the moment he's connecting, he's saying the galvanometer is deflecting. That means electricity is here. So then he realized that it only happens when you have a change in electricity. So changing electricity means changing flux. Changing flux means your changing flux produce or induce the electricity in the secondary coil. So that's what this equation was not developed by him. This equation was developed by Maxwell. But he's, again, one thing is that for Faraday, his whole life experiment as an experimental chemist, physicist, he never wrote any equation. He just wrote down his observation. All other after that came up with the equation. So this equation came up by Maxwell again, but that's just changing flux over here. So this changing flux actually induced the voltage in the secondary coil. So without changing flux, there is no induction of voltage. All right. So there's two different induction over here. One is transformer induction. If your coil is not moving, but you have a changing flux, that also can produce the voltage. That's called transformer EMF. If your flux is constant but your coil is moving, that is called motional EMF. Either way, you're producing a time varying flux. If you have both together, that's called EMF. Total EMF is transformer and motional. So let's say this is the coil over here, right? For this one, we're using time varying flux BT. So that going through this coil, and that's inducing a current, right? And also have your polarity here. So how do you know the polarity? If this is the DS on this one here, this is the DS, right? Differential area vector, right? DS over here. If your DS is your thumb, if you look at your forefinger coming from opening here, from crossing from positive to negative, that's how you define the polarity. So then I'll talk about the current direction later on. It's a different thing. So that's the polarity. So polarity is over positive and negative, and current going this way. We're going to talk about the next slide. So that's the polarity you design. You're taking the thumb as your DS with a differential area vector, and your four fingers crossing the opening, so positive to negative. That's the polarity, right? And so how to explain this negative sign, that will come into the next slide. So now, how do you know the current direction? So here's the thing: when this is the changing flux. This changing flux is induce a current here. That current will have a flux too, right? So that's called induced flux. This induced flux would be such a way that this flux will oppose the change in BT. So B induced flux will change the oppose the change in BT. It doesn't mean that it change is opposing the BT. It's only changing the opposite in BT. So for example, if your BT is increasing this way, the induction would be increasing other way around, right? So it's going down to increase, right? So opposing the change. To do that, your current going that way, right? So the current is going that way. That means your current is here, right? So you can see that your positive and current direction does not match. They're opposite to each other. That's why if you go back here, now that's the negative sign here. Can you see that? So there a current direction and a voltage polarity. Polarity came from here, and current direction came from your Lenz's law. They're opposite to each other. That's why negative sign. You see the negative sign, EMF, negative, and dB dt, right? dB dt. That's the negative sign. So current direction and your polarity is opposite to the current. That's why negative sign over here. All right. Again, B induced does not oppose BT itself. Is opposes the change in BT. So then this is okay. This is your B induced, right? Transformer here, right? B induced, and that is equal to this guy over here, right? So that is your for n equal to 1. That's your, we're using n equal to 1. That's the equation here. So this one can be written as this one over here using Stokes theorem, right? We have seen that in chapter 3. Then that means this one now equal to this one here, right? So that means you can go back to again your differential form of Maxwell equation for this particular induction. So they're saying this is the same thing. We can go back to that same equation again. And what is this equation over here? You have learned in physics 260 that your voltage is integration of electric field over a distance, right? If you plainly, you can say that B is E dot D, right? You learned them in physics 260. So in a closed path, so that's why you're doing closed integration over a distance dl. So let's see how it's working here. If you look at this one here, if you look at this over here, so your magnetic field going in the negative g direction, right? Negative g direction. So it's going if this is axis y, so this is the negative z direction, right? So in that negative g direction, your B is increasing over time. So in negative g direction, your B is increasing over time. So that means your induced magnetic field should be increasing in positive g direction. So your B induced, this is the B, right? I would say BT over here, right? And your B induced would be opposite direction to oppose that one. So that means your B is BT, this one here. So your B induced would be this direction, right? So that means coming out. It's coming out of the page. It's coming out of the page. Then your current should go this way, right? So that's your current direction. Can you see that? That's how you know what direction your current is going. So if your flux that inducing current is increasing in negative g direction, your induced flux should be increasing to oppose that, increasing the positive g direction. To do that, then your flux is basically coming out here. So then you have the current in a counterclockwise. So current is CCW counterclockwise. And we're going to do the rest of the math in the class. And for this one over here, this flux negative g direction, but is decreasing in negative direction, okay? Exponentially decreasing in negative g direction, exponentially decreasing in the negative g direction. So to oppose that decrease, your what do you call it? Your induced current should produce a flux that increases in the negative g direction. So your flux now should be what do you call it? Should be increasing in the induced flux should be increasing in the negative g direction, because in negative g direction your BT is decreasing, so induced flux should be increasing in this direction to oppose that change. That means if you do that over here, if you go forefinger is induced flux, now your current going this way. So can you see how it works? So your induced flux does not oppose the actual flux itself, which is the inducing flux itself, but only oppose the change. All right, so we're going to do this problem in the class. I think that's all for this lecture. We're going to do this problem in the class too. Yeah, that's all for the lecture 13. Again, remember that lecture main thing is that when a flux induce a current into a coil, that current also produce a flux. It's called induced flux. That induced flux opposes the change of the flux that's produced the current. All right, so that's the main thing over here.